In the following slides, I'll try to answer a few questions that my students been emailing me during the past few hours. The style is very informal and as time efficient as possible. We begin with preamble to BJT load lines problems both in DC and in AC. Then we move on to an op-amp question and finally a diode modeling question. Let's begin. The first question has to do with this configuration. One student asks, how is it that you find the Thevenin equivalent of this circuit and then connect that Thevenin equivalent to the circuit on the right? How is that possible? We learned in class that to find the Thevenin equivalent we needed a port, and the port was defined as two nodes, but here I see that there are three wires. You see 1, 2, 3. What's going on? Well, let's take a break first and see what happened. We have seen previously that we can connect two V sources in parallel only if they share the same value. And in that case, they are equivalent to a single ideal V source connected between those two points A and B. Because after all, what those sources are saying is we guarantee that A is higher than B by 7 volts. Well, we can achieve the same purpose with only one source. But the truth is that we can also convert a single source into a parallel, like this, of two sources with the same value. Can we? What do we do with that? Let's see. We begin with this circuit, one source 7 volts that feeds those two resistors in parallel. Well, if we can replace that source by two 7 volt sources in parallel, and we can draw the second parallel source 7 volts on the other side. After all, it's also in parallel with this one. What has changed? Nothing has changed. We're still guaranteeing that the point on the top of the circuit is higher than the one on the bottom by 7 volts. Well, we can do something interesting. We could, for instance, eliminate this wire here, and none of those resistors would really know if the change was made. After all, they see the same voltage, 7 volts, they see the same current and the same power. But now we can solve each one of the two resistors separately. How do we apply that? We begin observing that this circuit on the left is actually equivalent to the one on the right. Only one source between the reference node at the bottom and the node at the top, plus VCC volts. Well, let's replace that source by two sources in parallel. Let's connect the other parallel one down here with the same value, of course, otherwise it's impossible VCC. And then we say the node at the top on both sides is higher than the reference one by VCC volts on both sides. This wire at the top is redundant. And now we see that the two circuits are separated only by one port defined by this node and this node here at the bottom. This is the circuit we're going to find the Thevenin equivalent for. And that has, of course, as a Thevenin voltage, the voltage divider of VCC between those two resistors. That would be VCC times R2 divided by R1 plus R2. That is a V Thevenin. And our Thevenin we obtain by killing the source and looking into that port, and we see only R2 in parallel with R1. Let me write it down. V Thevenin is just a VCC times R2 divided by R1 plus R2, the voltage divider, right? And our Thevenin is what we obtain when we kill the source and we look into that port. We only see R1 in parallel with R2. And that is the circuit we will replace at the entrance of the base port. This one. Why is this so good? Well, because finding the base current in this one, which will be IBQ in this circuit, It's kind of easy. Check it out. This voltage is 0.7. It's known, 0.7 volts. We're assuming it's in linear operation. And then we say, the current here is going to be, in reality, beta plus 1, the value of that base current, right? Correct. So, this voltage drop will be that current times Re. This is that current times R Thevenin, and this is 0.7. We can write a KVL equation in that loop and solve for the current, and I invite you to do that, and you always get exactly this. That base current in that circuit is always the voltage applied by the Thevenin source found from this voltage divider circuit on the left minus 0.7. This drop in the linear operating transistor, that is our assumption, divided by the total equivalent resistance in this loop down here, which is R Thevenin and Re multiplied by beta plus 1. So we can use the same current on both resistors. So that is R Thevenin plus beta plus 1 that multiplies Re. Nice formula. And from there we just multiply that value, this one, by beta to obtain what is this current? ICQ. You see how fast and simple that is, just finding the Thevenin equivalent of what is on the left. Let's move on to the next question. So here's the next question. We have seen that there are two load lines. Here we have the DC load line with a slope whose absolute value is absolute of M1, and we have the AC load line with a different slope M2. We're interested only in the absolute values of those slopes. They intersect at that optimum Q point of operation, Q opt. One thing that defines that Q optimum is that it is so that along the AC load line, cut off down here, is at the same distance from Q as the saturation point up here. So that distance is the same. You see, this B is what separates Q from the saturation point, and B separates Q also from the cutoff level. But how do we find that B? How do we find the location of that Q point? Okay. This triangle here is exactly the same triangle of this one. That means that whatever distance we have, A, down here is the same distance this side of the triangle. On the top, this one. That's right. What am I going to do with that? Well, I can write this current, B, given that I know this distance from this point to VCC. Check it out. That is VCC minus 0.2 minus A. That is that distance here. VCC minus 0.2 minus A. And then what? And then what I do is I multiply that by the absolute value of this slope, and that gives me B. You see, like here, B is the slope in absolute value of that DC load line multiplied by that horizontal distance. VCC minus 0.2 minus A. That is one equation from the DC load line. But we can also compute B from the AC load line. That is A multiplied by the absolute value of the slope of the AC load line. B is absolute value of M2 multiplied by A. Two equations and two unknowns, A and B. Enter them in the calculator and just solve for A and B. And ICQ, the value of the collector current at the optimum Q, is just B. And who is VCQ? At this point, VCQ. Oh, that is just 0.2 plus A. Once you find them, you find your optimum point of operation. This next question is about op-amps. The question is, negative feedback happens when we have a passive element between the output and the inverting input. Yes, that's correct. But the question is, Are those the only elements that provide negative feedback, that is, passive elements, resistors, inductors, and capacitors? No, not really. They are a sure bet, but in other cases we have to prove whether there is negative feedback. Let's try an ideal V source in the negative feedback loop and see whether that V source really provides negative feedback. I will make no assumptions. I'll replace the op-amp by its model. Infinite input, that's right. Zero output resistance. Infinite input resistance. And the output is A times Vp minus Vn. I'm not making any assumption about the value of A. Well, that is the circuit. 10 kilo ohms here. A 2 volts ideal independent V source. Let's solve that circuit. And evil equation, V naught is Vn plus 2 volts. This one. And this one, that is a KCL equation for node N. This current, Vi minus Vn over 10 kilos, that is equal to the evil current Ix. Fine. And this one, well, that is a KVL equation for node P. Vp is 0. And last, this one, an evil equation for this branch. It says this voltage V naught is the reference voltage plus this source. That is, this one. We solve that system of 4 equations and 4 unknowns, and we find, among other things, what we're interested in is finding Vn and finding Vp. Vn is negative 2 divided by 1 plus A for any value of the gain of that op-amp. But now, if we let A grow towards infinity, Vn decreases towards 0. Indeed, an ideal V source also provides negative feedback. So every time we have that, we also have negative feedback. By the way, it's not hard to prove that the same happens with a controlled voltage source. So as long as you have a V source here, or passive elements or combinations of them, we have negative feedback, and Vp is equal to Vn. The natural sequel to that question is, what if what we have here is not a V source? What is what we have there is a current source? Let's see. Well, let's see here. We have replaced the V source by an ideal current source of 2 milliamps. As we can't make any assumptions, I've replaced the op-amp by its model. Same as before. But in this case, observe that the current through this 10 kilo ohm resistor is 2 milliamps. So that means that there's a voltage drop in this resistor given as Ri. 10,000 ohms multiplied by 2 milliamps. That is 20 volts. That means that N is lower than the input by 20 volts. Vn is in reality Vi minus 20 volts. You see that here? So unless Vi happens to be exactly 20 volts, the voltage Vn is not going to be 0. It's not going to be equal to Vp. So in general, the current source up here does not provide negative feedback. Whenever you see a current source there, independent or controlled, there is no negative feedback, at least not due to that source. Maybe if there is a resistor in parallel with that one. Possibly. Well, and let's move on now to the last question. The last question is about diodes. The student asks, well, if a regular diode, a rectifying diode, can be represented by this model, a 0.7 volt source in series with a resistance, who are they? If we go to the graphical approximation of the behavior of a real diode, we see that that approximation intersects this horizontal axis and the V value of 0.7 volts. And the inverse of that slope is what we call the dynamic resistance of the diode, which is the value that we use in this representation. So that's how we came up with that model, and we justified in class why that was so. But the student asked, well, what about the Zener diode? In the Zener diode, we are not interested in operating in the forward area of operation. No, we operate here in the reverse mode. That is where we find the Zener diode, and because we're going to be working there, we will define a positive voltage in the Zener diode with this polarity, like that, and a positive current in the Zener diode with that polarity. That is, we're going to be operating somewhere on this line. That's why let's turn around this graphic and draw it rather like this. Positive IZ, positive VZ, and this is the line. You agree with me that we could represent that Zener diode with a V source of a value Vx in series with a resistor that is the inverse of the slope down here. We call that RZ at the test point, RZT. Sure, we could represent it like that. Vx in series with RZT, the dynamic resistance of the Zener and the test point. Here, that value is given. This value is given. However, Vx is not given. What they usually give us for the Zener diode is the voltage of the Zener at the test point, this one up here, and the corresponding current IZT. We do not know Vx, so we do not know what value we use in the model. But that is not too hard to compute, as we have seen in exercises and assignments. Vx is just the Vz at the test point minus this little difference in the voltage. How much is that value? That value is IZT multiplied by this resistance, right? Given the slope, that's how you find that one. You subtract that from VZ test and you get Vx, and with that Vx you can actually model the Zener diode. This answers the last of the questions that I had received in the past few hours. Thank you very much.